he's a sixth-year PhD student working with Merrick at the Northeastern University in Boston.
Yep.
And he's supposedly graduating, right?
Yep.
Did your advisor promise you this?
Yeah, I've got his promise.
Okay, so you can hire him in a few months, okay?
Thank you very much.
Or not? Oh, I'm going to ruin your graduation.
That's fine. Okay, great. Full mode. Thank you. Okay, thanks. All right. Okay. Wow, it's bright. All right. My name is Rundong. I'm from Data Lab at Northeastern University. This is a collaborative work with my advisor, Professor Mirek Riedwald, and my colleague Xinyan. So first, I want to introduce the tool we used to illustrate the join of two relations, S and T. So in this join matrix, each row is conceptually an S tuple, and each column is a T tuple. So the intersection of a row and a column is marked green here to show that they have the same join key. And for example, the 4 S tuples and the 5 T tuples marked there, they share the same join key 1, so they are to be joined with each other, and we call them join group 1. And so for distributed execution of joins, we have to assign different join groups in this matrix onto different machines. And in this case, because of this giant join group 1, we cannot do a better load balance. So to deal with this problem, we have to partition these so-called heavy hitters and assign the subgroups to different machines for a better load balance. But pay attention here, we have this comes at a price. So by doing a partitioning, we create some extra data duplications, and the total load will increase. And sometimes we don't want to do that, and there's a trade-off between the load balance and the total load. So we'll come back to this trade-off later. And let's see how state-of-the-art algorithms partition these heavy hitters. So the first one is called partition broadcast. It existed since the dawn of distributed databases, and 10 years ago, Xu et al. Revisited this problem, and this algorithm is actually a heuristic without any optimality guarantee. So the second one was proposed more recently by Bim, Kuchis, and Suchiu, and the algorithm is more complex and has some optimality guarantee. But the algorithm is only asymptotically optimal. What we want, actually, is some guarantee that the solution is within a small constant factor of the optimal. Okay, let's see how we approach this problem. So we take a probabilistic perspective. Think of the groups and the subgroups. They are assigned to the machines randomly. And now let's look at the load on each machine. Now, the load on each machine is a random variable now, and it has expectation and variance. Okay, given two subgroup partitionings with the same load expectation, we prefer the one with the lower variance, because in general, lower variance means better load balance. Okay, next we define a optimization problem, which is to minimize the load variance subject to some limit on the load expectation. Okay, so careful analysis makes us find these two nice properties of variance. Okay, so first one is monotonicity, the second is submodularity. And these two properties will hold when some conditions are met. In practice, these requirements are easily satisfied, which means that we, in practice, will almost always have these two nice properties. Actually, this is our key result, and we spend a fair amount of time to derive all these proofs, but due to time limit, we're not going through the details. And these two nice properties turn this problem into a monotone submodular maximization problem with knapsack constraints. And for this type of problems, we have a simple greedy solution, which has a small constant factor approximation guarantee. And it's a greedy solution. In each step, it makes a greedy choice by maximize the ratio between variance reduction and the input duplication increase. Let's see how this works using a simple example. So here we see 5 join matrices and shows the 4 steps of our algorithm. In each step, we add one partition to one of the heavy hitter groups. And where do we put this partition depends on which one can maximize this ratio. Okay, and we use the help of a cost model to monitor and estimate the running time whenever we add one more partition. Okay, and this chart below shows this process. And from left to right, we add more partitions, and the purple line above there shows the trend of the running time. And we can see, at first, when we add more partitions, the running time drops significantly. And but on the other hand, if you look at the blue line in the bottom, it keeps increasing. This is the average load. It keeps increasing because we create more and more duplications. And so there's a trade-off between this variance and this total load. And we can see the running time eventually starts to increase because of this extra duplication. So we use the help of a cost model to help us decide when should we stop partitioning and obtain the shortest running time. Okay, now let's see some experiment results. So we test our algorithm on a range of synthetic and real-world data sets with various data scheme. And we also compare our algorithm with 4 others. First one is just a simple classic hash join. And we also included the 2 state-of-the-art algorithms we mentioned before. We also improved these 2 algorithms, used the help of cost models. So we can see on each data set, our algorithm wins. Okay, and conclusions. So far I have covered how we come up with near optimal greedy partitioning strategy. And due to time limit, something in our paper we haven't covered. So the first one is our algorithm really works well for even deterministic load assignment. And all it needs is some simple statistics about the heavy hitter groups. So in the future, we're going to expand our algorithm to support multi-way joins. Okay, that's it. Thank you.
Time for questions. Okay, so if you want to expand from multi-way joins, like, I mean, you obviously haven't done it yet, or maybe you have. Like, what's the magic secret to make it work?
Actually, the simplest idea is just to pick the right join order. And there are also other previous works on how to do this multi-way join in one operation. And we're looking into that, but so far I cannot say I have any good idea about that.
You just implemented this in a testbed system for yourself? You thought about implementing it like in a Presto or some larger SQL processing system?
So far, I've been writing programs on myself, and I haven't thinking about how to expand it to a large system. But I think in principle, it can be implemented in any distributed database systems, and even Spark or Hadoop.
You need to graduate, so you can't do that, right?
Probably in the future.
All right, any other questions? Thank you again.